All right, let's jump right into this explainer by tackling a very real fear that grips millions of travelers every single day: the physics of exactly what keeps massive metal tubes suspended high up in the sky. If you've ever gripped your armrest during turbulence and thought, how is this thing actually staying up here? Well, you are in the perfect place. We're going to break down the hard science and the aerodynamics that make flight not just possible, but incredibly safe.
To kick things off, we found this incredibly relatable Reddit post from a focused learner who is, understandably, absolutely terrified of falling. They're asking the fundamental question that kind of sits at the back of all our minds, right? If something goes wrong, say the systems fail or the engines just stop, why doesn't the airplane just drop out of the sky like a stone?
And honestly, that is a completely fair question. I mean, think about a fully loaded Airbus A380. That thing can weigh around 560 tons. It's totally natural to assume a mechanical failure means gravity is just going to immediately win. How on earth does a giant iron bird counteract the pull of the entire planet? Well, to understand why it doesn't just fall, we actually have to totally change how we think about the sky itself.
So first up, air is a physical fluid. Most of us just walk around thinking of the space around us as, well, empty, right? A vacuum of nothingness. But in the world of aerodynamics, air is a very real, physical substance. Much like the water that holds up a massive cruise ship, air is a fluid. It has mass, meaning it has momentum when it moves. It has pressure. It's packed with billions of individual molecules that can physically support immense weight if you know how to interact with them. It's literally an ocean. We just happen to be walking around at the very bottom of it.
If you look at the kinetic theory of gases, it shows how these air molecules are just constantly smashing into each other, transferring momentum all over the place. And here's a fun fact. This is actually what you're feeling when you hit turbulence on a flight. You aren't hitting empty pockets of nothing, you're just flying through shifting currents of a very real, dense fluid pushing against the aircraft. NASA actually points this out perfectly. Without this physical fluid interaction, aerodynamic lift is literally impossible. Lift is a mechanical force. It requires physical contact with the air. No fluid, no lift. It's exactly why the space shuttle stays up in the vacuum of space using orbital mechanics and raw speed, rather than its wings. Out in space, there's just no air to push against.
Which brings us to section 2, the balancing act of the four forces.
So once we accept that air is this thick, physical stuff we can push against, the dynamic equilibrium of flight starts making a lot of sense. For an airplane to fly straight and level, it's essentially performing a massive balancing act between four distinct forces. You've got weight pulling the plane down towards the earth, lift pushing it up, thrust from the engines pushing it forward, and drag, which is basically air resistance, holding it back.
For a plane to just cruise steadily without speeding up or slowing down, these forces have to perfectly cancel each other out. Thrust has to exactly equal drag to keep the speed constant. And, crucially for anyone who hates the feeling of dropping, lift must exactly equal weight to keep the altitude steady. When these forces are balanced, the plane is in perfect equilibrium. Physically, it just cannot fall.
And here is the really mind-blowing part about how efficient this balance is. In normal cruising flight, the lift-to-drag ratio is typically around 15 to 20. That means for every single pound of thrust the engines pump out to push through the air, the wings leverage that fluid to lift up to 20 pounds of weight. The wing is essentially acting as a giant, hyper-efficient aerodynamic lever.
All right, section 3, the lift generator.
So, how exactly does a wing manipulate that fluid to create lift? We know it's a lever, but what's the actual mechanism? Well, we can actually measure it with pure physics. The Journal of Young Physicists highlights this formula. Lift equals half the air density times velocity squared times the wing's surface area times the lift coefficient. Okay, I know, don't panic, there's no pop quiz on the math here. The main takeaway is simply that lift isn't magic. It's a highly calculated, deliberate manipulation of speed, shape, and air density.
When you look at how air flows over a wing or an airfoil, you're basically seeing Bernoulli's principle and Newton's laws teaming up. The specific shape and tilt of the wing create faster, lower pressure air over the top and slower, higher pressure air underneath. So the high pressure underneath pushes up, while that lower pressure on top effectively sucks the wing upward.
So putting that all together, a wing generates lift through a specific combo of three things: flying at an angle of attack, creating that pressure differential we just talked about, and actively redirecting air downward. By forcing all that air down, Newton's third law kicks in, dictating that the air absolutely must push the wing up in response.
You know, you've probably tested this yourself without even realizing it. Think about the classic hand out the car window analogy. Next time you're on the highway, just tilt your hands slightly upward out the window. The fast-moving air hits your hand, deflects downwards, and your arm gets pushed up, right? You are quite literally experiencing aerodynamic lift firsthand.
Moving on to Section 4, Built to Fly. Let's talk about stability and stalling.
And this is where we get into the ultimate reassurance if you're a nervous flyer. What happens when things actually go wrong? Say the plane slows down too much, or the pilots literally take their hands off the controls. I absolutely love this quote from an aviation enthusiast on Reddit. Fish gotta swim, planes gotta fly. An intact airplane physically wants to stay airborne. If you let go of the controls, a well-designed commercial jet will naturally try to level itself out. It literally cannot not fly as long as it has forward momentum.
The way this built-in stability works is basically just like a giant playground seesaw. Engineers specifically design planes so that the heavier center of gravity sits slightly in front of the center of lift. The tail of the aircraft then acts like a smaller counterweight pushing down, perfectly keeping the nose level. Because engineers designed it this way, with that heavy nose, if a plane slows down way too much and loses its lift, which is called a stall, it doesn't just belly flop out of the sky. Instead, that heavier nose naturally drops down. And when the nose drops, the plane speeds back up, catches the airflow again, and lift immediately recovers all on its own. The plane is quite literally physically designed to save itself.
Okay, but what if the engines completely fail? Do you just drop then? Actually, no. The plane just becomes a massive, incredibly efficient glider. The pilots just pitch the nose down slightly, and gravity pulls the plane forward, totally replacing the job of the engines. This isn't just theory either. This is exactly what happened with the famous Gimli glider, a commercial flight that completely ran out of fuel midair, but glided perfectly to a safe landing without a single engine running.
Now, obviously, planes don't just fly perfectly straight all the time. Turning actually requires some extra force. When a plane banks to make a turn, a chunk of that upward vertical lift gets diverted inward to pull the plane around the corner. So to keep from descending during the turn, the pilot has to pull back and increase the angle of attack. That creates more total lift, which is exactly what you're feeling in your seat when you experience those G-forces pushing you down.
Now, these physics rules beautifully govern how a plane flies right up until it hits transonic speeds, which is when it approaches the speed of sound. At that point, things get a little wild. The air is moving so insanely fast over the wing that it can't even get out of its own way. It actually starts to compress and form physical shock waves, totally changing how drag and lift behave. But don't worry, standard commercial flights stay well within the safe, totally predictable subsonic rules.
So what's the big takeaway from all this? Basically, an airplane's sheer shape forces this giant physical ocean of air to hold it up. As long as it maintains that shape and keeps moving forward, the air essentially has no choice but to push it upward. And modern commercial aircraft are built so incredibly tough that they easily maintain that shape through even the most extreme conditions.
So, now that you can actually visualize this dense, invisible ocean safely holding up your flight, are you ever going to look at gravity the same way again? You aren't defying gravity up there. You're just using an invisible ocean to securely balance against it. Thank you so much for joining us for this explainer, and we will catch you on the next one.